Good evening. My name is Michelle Judd. I'm the Managing Director of the Keck Institute for Space Studies, and I would like to welcome you to this very special event, which is co-sponsored by the United States Geological Survey and the Planetary Society. The Keck Institute for Space Studies is a joint institute between the Caltech campus and NASA's Jet Propulsion Laboratory. We bring together experts from all over the world to study new ideas that could possibly impact future space missions. If the study identifies a possible breakthrough in technology, we then provide seed funding to see if that breakthrough can actually be achieved. This week, the Institute is running a study on monitoring Earth surface changes from space. And we thought that, well, while we had all of this exceptional talent in town, that we'd take advantage of them and allow you, the public, to hear the latest news about these two earthquakes. Before we get started, I'd like to just cover a few items. The first is please turn off all your cell phones. We are filming tonight. I'd like you to all also hold your questions until the end. We'll have an open question and answer session, and we're also taking questions via Ustream TV, the chat room. Given the situation of the earthquake in Chile, the Chilean community gathered and organized a joint effort between the Caltech Y and the Caltech Latino Association of Students in Engineering and Sciences to raise money that will be sent to Chilean-based relief organizations. Please feel free to drop by after this event if you'd like to make a donation or you just want to hear more about how you can help. Our moderator today is the chief scientist of the USGS Multi-Hazards Demonstration Project for Southern California. She is also a member of the California Earthquake Prediction Evaluation Council. Please help me give a warm welcome to Dr. Lucy Jones.
Thanks, Michelle, and thank you all for coming. Hope we have a wonderful evening together and a time where we can share with you what it is that we find so interesting about studying earthquakes. In fact, a little bit more than that, we're going to be looking tonight at modern methods for studying earthquakes and the ways in which new technologies in space science have really changed what we can see on the Earth, what we can see after an earthquake, and how fast we can see that, and therefore how much we can help the recovering community. You're going to hear tonight about both space methods of looking at earthquakes and field methods of looking at earthquakes, and we can see how each of them contributes its piece to understanding what goes on in the events. A lot of you are here probably because you really think science is cool, and so do we all. There's also reasons, however, as Californians that we need to take this seriously, because this year the communities that suffered were in Haiti and in Chile. Our turn will be coming, and we can hope that when our turn is here, that these technologies will be at the point that they can really help us. Because one of the things that we can learn out of both the comparison of Haiti and Chile is that it's not the magnitude of an earthquake that determines whether or not it's a disaster. Right? The magnitude tells you how much energy was released, and the Chilean earthquake released 500 times the energy of the Haitian earthquake. But whether or not it's a disaster is how it affects our communities and how it affects our buildings and our society. And that has a lot more complicated pieces than just what the magnitude is, including how close people are to the shaking, how strong the shaking is, how long it lasts, but also how their buildings respond, how their society responds. And all of those play together. So even though the Chilean earthquake was 500 times the energy of the Haitian earthquake killed 300 times as many people. And you'll see a bit as we go through tonight both how we study these events and why some of that huge difference shows up between the events. And I hope it all will lead to lessons we can learn for when it's our turn. So let me go on right now to introducing our first speaker. That's Professor Mark Simons, who's a professor of geophysics in the Seismological Laboratory here at Caltech. He got his PhD from MIT. So did I. I think it's a pretty good place to go. And he also then came and he served as a postdoc here at Caltech before he became a professor. So he works very extensively with colleagues both at JPL and with the USGS to exploit this revolution in Earth observing as it's applied to the study of earthquakes. Mark?
All right, good evening. It's a pleasure to be here and to talk to you about what I think is a very exciting period in our ability to understand and monitor and react to these large events. Tonight, we'll describe a variety of these new technologies. Many of them are space-based. Of course, we will also have ground-based methods, geology and seismology. And we'll try to describe how the combination of these methods can actually give us unprecedented detail of what actually happened during the earthquake, what happened in the subsurface on the fault based on measurements made at the surface. Tonight I'm going to focus myself primarily on the magnitude 8.8 earthquake that occurred in southern Chile just over a month ago now. Subsurface rupture extended over a region nearly 500 kilometers or 300 miles in extent. Here I show the aftershock distribution that occurred over the first 10 days relative to the scale of all of South America. You can see that the impact of this area is quite extraordinary. The amount of information that we've learned in this last month is also quite extraordinary and unprecedented. And it really sort of represents a new phase, whereas what we used to learn in a year or 2 years of analysis, we can now do in a month. And then you can let your imagination run wild and say to yourself, well, maybe in 5 years' time, 6 years' time, we can do the same thing in a day or in a half a day. And then when you start to do that, then you can start to ask yourself the question, how much can we use the kind of information you're going to see here to help actually assess what just happened in an event very rapidly? To what extent can we help the response to save lives? And to what extent can we help the recovery phase and the rebuilding phase? And that'll be a recurring theme throughout both my presentation and the other presentations that you see. All right, so first let me give you a bit of context. As a geoscientist, we have many modes of activity or facets to our daily life. We are particularly good at this discovery phase of trying to say what just happened and trying to understand the mechanics or the physics behind what just happened. If you do that well enough and you understand the system well enough, you can then move on to trying to sort of make some kind of prediction. Where do you expect large earthquakes to occur in the future? On what kind of time scale should we expect them? What size should we expect them to be? Using that, you can then also say, well, if I expect a large earthquake, how do I prepare for it? How do I mitigate against the risk associated with the earthquake hazard? That, of course, is primarily an economic, engineering, and education decision. But that is all based on actually having a good understanding for what the process is. Given that, we can also deal with the response mode, as I alluded to earlier. And today, I think what we're going to focus on primarily are these first and last facets, this discovery phase of what happened, how do we use these technologies to really understand what happened, develop an understanding for the physics behind that, although we probably don't have that much time for that today. And then we'll let you sort of creatively think about, although I will allude to it towards the end, about what we could possibly do if we did everything we've just done in the last month or the last couple months if we shrank that time scale down to a day. All right. So let's get some more geophysical context here. First of all, as you all know, we live on a planet which is characterized by plate tectonics, where plates move around at scales of a few centimeters per year or a few inches per year. The largest earthquakes occur generally where these plates converge and collide, and the predominant way that they collide is in what we call a subduction zone, or a subducting plate, where one plate actually dives down below another plate. In Chile, the Nazca plate subducts underneath the South American plate. If you look at the top 6 earthquakes that have occurred in the last 100 or so years, what you'll notice is that they are all on subduction zones, ranging, and here I've just shown you the earthquakes in magnitude 8.8 and larger. Many of you may be familiar with the Chilean earthquake of 1960, which is the largest earthquake in instrumental record. Although it is, for us, it is still in some sense the dark ages of geophysics, because there was still very little instrumentation around. You also see listed the 2004 and the 2010 earthquakes, the Sumatran earthquake and the Chile earthquake. Those are important because they are the largest earthquakes to have occurred in this modern instrumental era. But more importantly, in fact, the Sumatran earthquake occurred mostly underwater and under islands. The Chilean earthquake is unique because you actually have the whole South American continent available to you from which you can make observations about what happened in the subsurface. So this earthquake promises to be one of the more important earthquakes we've seen in a long time because of the extreme amount of data available for it, data that was taken before the earthquake, after the earthquake, so that we can see what the changes were, as well as the ability to monitor what happens as a result of the earthquake over the hours, days, weeks, and years to come. What happens during these large earthquakes is that between earthquakes, the subducting plate actually moves towards the overriding plate, and it's stuck, and it doesn't slip. And so what it does is it actually squeezes together this overriding area here. During the earthquake, this place unsticks, it becomes uncoupled, we would say, and it elastically rebounds, and so that the plate that's overriding will jut out towards the ocean. And in fact, as you'll see in a little bit, the South American continent moved at least 3 to 5 meters or 15 feet into the ocean as a result of this earthquake. Now, of course, this is an area which is not new to having large earthquakes. They've occurred for millennia, and they will continue to occur. What I've shown here for reference is the topography of western South America. You can see the Andes. This is directly attributable in the long run to the subduction process. What I've shown over here on the far right is the last 80 years or so, or 100 years of large earthquakes. The ellipses indicate sort of the approximate area that we think slipped during these large earthquakes. And you can see these are all magnitude 7.5s and larger. I won't list them all, but you can see lots of 7.5s, 8s, 8.4, 8.4, 8.1. This is the 1960 earthquake, which ruptured over 1,000 kilometers, or close to 1,000 kilometers. And in purple, light purple here, you can see the approximate area of the 2010 earthquake for scale. Okay. So the 2010 earthquake was very large, but not as large as 1960. This also gives me the opportunity to mention or clarify a few points which I think are frequently forgotten. When we talk about earthquake size, we frequently talk about the magnitude of the earthquake. The magnitude of the earthquake is a number which is derived for convenience, but it is actually based on something we call the seismic moment, which is telling you really about the energy of the earthquake. And it's very simple, actually. It is just simply the area of the fault that actually slipped in the subsurface, how much it slipped, times the strength of the crust. What is the strength of the spring or the elastic properties of the material that surrounds the fault? If you assume this rigidity or this elastic properties are relatively constant, what you find is that the size of the earthquake or the magnitude is really directly related to the amount it slipped and the area. Large earthquakes slip larger areas and slip more. The energy is then related to this moment, and what you see, as Lucy mentioned earlier, is that this Chilean earthquake was a factor of 500 more energy than the Haitian earthquake, for reference. So now, of course, this is an area that has a lot of seismicity. This is including very small earthquakes, magnitude 3s and so on. This is the last 100 years of seismicity in the region that had the magnitude 8.8 earthquake recently. So you can see this is quite an active area. The earthquake started right here at this star, so there's no surprise. If we take a cross-section through the Earth along this white line here, so now here we have depth into the Earth and distance along that profile, and we look at where all these earthquakes are, you can see they delineate beautifully the location of this interface between the two plates. And so what you're seeing is really the seismicity helps illuminate the geometry of the system, something that will be very important to us later on. A similar figure is shown here, where you can see in yellow the aftershocks from the 2010 earthquake, and in hatch area, the area of the 1960 earthquake. And you can see that to a large extent, these two areas slipped mutually exclusive areas. However, as I said earlier, this 1960 earthquake occurred in a time when we didn't have very many observations. And so it's a hope that an event like this one here will not only help us understand what's going on in this region, but will also help us understand more what happened in the past in 1960. Now, this historical context is, of course, very important because the recurrence time of large earthquakes is hundreds to thousands of years, depending on where you go. And so you must always take a historical perspective when you address these problems. Now, we can go beyond 1960, in fact. We can go back to Charles Darwin. This event is actually a very interesting event to us because it appears that it may be a candidate for a recurrence of an earthquake that Charles Darwin felt back in 1835. It's beautifully documented in the Voyage of the Beagle. If you go to chapter 14, you can go download this from the internet. You just go Google search Voyage of the Beagle, and you'll find a very vivid description of an earthquake that he felt. And I've outlined a few things that are salient here. And the question that we're going to ask ourselves over the days, weeks to come is to what extent was this earthquake, in fact, the same or close to being the same as the earthquake we just experienced in the last month. So what did he find? Some of the things he points out is that he was sitting in Valdivia, which I'll show you in a map in a second, but that's at the southern end of the rupture for this 2010 earthquake, at the northern end of the 1960 rupture. And it said the shaking lasted a good 2 minutes, but appeared to be much longer. Captain Fitzroy was in somewhere else further north on the coast, made the point, which is actually very important to us, is that the houses did not fall in general because they were wood frame houses. Right? That's maybe a lesson that we should learn from. He does describe the tsunami as being a slow but persistent process. He mentions that if you go to the Bay of Concepcion, which you'll see also in a second, he's noticed that the shoreline was uplifted 2 to 3 feet, or about a meter. There's an island offshore, Isla Santa Maria, where Fitzroy noticed that if you looked at barnacles or corals, that they were now sitting 3 meters or 10 feet above sea level. Right? So these are kinds of observations that we can actually compare directly to. We can actually make point-for-point comparisons with the measurements in 1835 with what happened in this recent event. And that's ongoing by a variety of workers. And similarly, and maybe more impressively for those of us who study long-term geologic processes, was his inference that, in fact, this earthquake and the processes related to this earthquake were probably very inextricably linked to the long-term evolution, geologic evolution of the region and the formation of mountains, which was quite a leap. All right, so the kind of questions that we have, for instance, include things like, all right, if I look at the fault plane here face on, so this is down the fault and along the fault, are the places that are stuck, small little pins on the fault that are stopping it from slipping? Are there medium-sized regions, or are there very large regions which are all clamped together? Of course, if this is the case, the likelihood of having very large earthquakes increases dramatically. And so what we'd like to know is what is the character of the fault surface. Does it look like this, or does it look like this? So how much slip, we'd like to ask how much slip occurs on a spot, and how much of these areas, and by looking at what happens during the earthquake and after the earthquake, how much do these areas stick, and versus how much do these areas creep without generating earthquakes? Now, until recently, seismology was the primary tool of choice. You could use seismometers distributed around the globe, look at the waves that traveled through the interior of the planet, and you could use them to forensically interrogate what actually happens on the fault surface. And that worked reasonably well, but it has a variety of limitations, which hopefully the new technologies will help us take care of. So these are the kind of technologies that we're using. We use GPS, although a fancy version of it. You'll see examples of using lasers, although it'll be called LIDAR, based on airplanes or satellites to measure fine details of the Earth's topography. You'll see use of optical imagery, and you'll see use of radar. Hopefully you don't see this kind of radar much in your life. Ours will be a little bit more sophisticated than this. And all of this stuff will go into your computer. Now, our version of this is a little bit fancier. We have radar on satellites. We have, eventually in the next year or two, we'll have radar on uninhabited vehicles. We have these GPS attached permanently to the ground that can give you millimeter per year accuracy in absolute coordinate system. We have optical satellites. We still have seismology. I didn't show a geologist. I should have shown a geologist up here. It's hard to stick the geologist into the computer. We have computers, and this is actually the computer in our basement. And this is very important because we're also facing a revolution, not in observation, but also in computational power. This is 4,000 CPUs that individual students and faculty use on a daily basis. And then that all goes into the graduate student. All right, so now let's talk about what actually happened during this earthquake. And I'm going to do this, I'm going to explain, first of all, the concept of the earthquake cycle. This is using GPS observation, and we're going to look at this at various time scales. So the time scale here is the days, day of year, from 50 to 80 years. And you can see a period before the earthquake, during the earthquake, and after the earthquake. And I've shown it for 3 components because, of course, the ground can move in 3 dimensions. And so you're looking at the vertical, north, and eastern components. So we have the interseismic period. This is kind of language that we use rather loosely. The co-seismic period and the post-seismic period. If we look in detail what actually happens during the earthquake, at this one site here in Concepcion, you can see 3 meters of movement to the east. And let's look in details here. This is truly remarkable. This is now using GPS like a seismometer, where you can actually make estimates of your position every second. And you can see, if you did take the difference between where you are here and where you are down here, that's the same thing as this 3-meter differential. But here now what you're seeing is the whole evolution of the slip on the fault as measured at the Earth's surface. You're being able to see the seismic waves, and you're actually able to see how the fault actually got from one position to its next position. You can then also look at the post-seismic period, something we won't focus much on today for lack of time. But I just wanted to point out that if we look at the first 20 or so days after the earthquake, for instance, at the same location here, it's hard to see at this scale, but it still continued to move. And at the surface, 40, 50 kilometers away from the fault, the surface still measured 18 centimeters, 20 centimeters of motion in the first 20 days. Right? So it's a very dynamic place. All right, so let's focus on what happened in the co-seismic. Here's again a picture of all of South America. With the co-seismic displacements as produced by colleagues at the University of Hawaii, and you can see how even Argentina moved a few centimeters. This is a discontinuous line because on this scale you wouldn't be able to see 3 meters out. If we zoom in, one of the interesting things I'll just mention in passing about the post-seismic is this is that post-seismic deformation that you saw earlier. It's significant, but what's also interesting is that it's not in the same direction as the co-seismic. What that means is not just that the earthquake keeps going, it means that different parts of the fault are slipping after the earthquake than what happened during the earthquake. And this, for us, is very exciting because it really gets to the mechanical behavior of the fault interface, and something that will be the source of a lot of study in the days and months to come. All right, so we're left with these questions that my colleagues are going to discuss, hopefully, in various detail. Basically, what fault slipped? How much did it slip? Where did it slip? And what are the implications of that slip? That's really what we're really after tonight. But before letting them take the stage, I just want to mention a few things here in closing. One of them is because this is such a unique event, such an important event, there's been a lot of effort by the community to go instrument this area further, to look at the response of the Earth to just having its insides kicked. And so each of these triangles is a GPS monument. And the red triangles are actually 20 continuous GPS receivers running at 1 second or faster that have all been installed in the month after the earthquake. Similarly, we're going to talk about radar data. In a second, actually, I've lost a slide. Radar data, and we're going to see that there's extensive imaging of the Earth's surface from radar satellites that will also provide us a new view of what happened during the earthquake. 1 second here. Okay. I'd like to point out in closing here, one point here, that as these technologies come online, what you're going to see is that not only will these kinds of observations, the GPS and the imaging data that you'll see in the next presentation, not only will they become more common, you'll see the latest GPS result on the news perhaps. That's not as important as, in fact, that as we can shrink the amount of time required to make these analyses, we will be able to have a distinct impact on the rapid response and assessment. And the hope is to be able to work with agencies such as the USGS, Homeland Defense, and so on, and to be able to actually enable both domestically and internationally the response to these large events using this technology. So with that, I think we'll move on to a discussion of a modeling effort for this earthquake. Thank you.
Thank you, Mark. Well, thank you. I hope that helps you get the context and the fundamentals of the earthquake, that we can now go and look at what the different type of space measurements have been. And note how Mark started from Darwin. The ability here to actually be able to do a repeat experiment over a couple hundred years of the seismic cycle is going to lead to some really interesting results as we take these things that are here and being able to compare them back. You're going to hear the first round of this from our next speaker, who is Dr. Anthony Sladen. He is a postdoc in the Seismo Lab, as Mark was a while back. Well, actually, he's just moved on. He's now a research seismologist. He's gotten a more permanent position within the lab. He got his PhD in Paris at the, I'm not even going to try, University of Paris. I'm not going to try and do exactly, my French accent doesn't deserve to be listened to. So, Anthony Sladen.
Hi, everyone. Thank you for this nice introduction. So tonight I would like to report on a joint effort done at Caltech with many other people. I won't have time to mention all of them, to try to get a sense of what happened really during the earthquake. So as Mark said before, this event is, for seismologists, is probably a key event because it's big, so we have the opportunity to see everything at much finer scale and to maybe grab the details of what's causing the earthquake. And also because it comes at a time where we have all these new technologies like GPS and INSAR, which are just about to release their full potential to study earthquakes. So this is the figure that Mark just showed before of GPS measurements. So you have sites here in Argentina which move by a few centimeters to the west. You can see that basically all these vectors are kind of aligned, so they don't have much sensitivity to what's happening really along the rupture. Whereas if you look at those vectors, they're pointing in different directions, which means they're sensitive to the details of the rupture. But the problem with GPS is that they don't have a very good spatial coverage. And to compensate for that, we can also use INSAR. So INSAR is basically imaging the ground before and after the earthquake, and by looking at the different subtle differences in the radar images, you can track the motion of the ground. So here you have one of those images, which is just a combination of an image before and after the earthquake. And you can see places like here in the north of the rupture, which move by a few meters. And so by combining this type of data with GPS, we can get an estimate of the details of the rupture. But to do that, before we need to know the geometry of the fault. So here I have a movie which was done, and I would like to thank Francisco Ortega for making this movie. It's a 3D movie of the interface between the South American plate, which is here, and the diving Nazca plate. And so to know the geometry, we're using the earthquakes. Because as Mark mentioned, the earthquakes are, and you can see them, all these dots here, they're illuminating this interface. And so by using their location, we can track the fault geometry in 3D. So here, all the yellow dots are the aftershocks of the Chile earthquake, and all the white dots are the continuous seismicity that has been going on for many, many years before the earthquake. So combining all these data, we get the geometry. Supposed to move, yeah. Here it is. And now we are going to zoom on the area of the earthquake, and you have the epicenter here represented by this light green ball. Okay, as you can see, the aftershock nicely delineate the area of the earthquake. And here I'm going to show the results of the combination of the GPS and the INSAR to see which area on the fault plane actually moved and by how much. So here you have the epicenter. The red line is the coastline. So you're looking up, you're looking to the west. So you can see that you have slip on both sides of the epicenter, which means that the rupture was bilateral. You have actually more slip to the north, with about, you see on these red spots, it's about 19 meters of slip on the plate interface. And some slip also to the south, maybe smaller amplitude. And so I'm not going to show you that, but from this model, we see that most of the area which is uplifted by this earthquake is actually offshore, so in this area. And if you remember the quote from Darwin, he mentioned that Isla Maria, which is an island just here, moved by 1 meter up. And from these modelings, we tend to see the same amount of uplift. So this might be an indication that this earthquake, at least for the south part, was a repeat of the Darwin earthquake. Of course, this is a preliminary study, and as we get more data, the model will be refined, and maybe we'll get a different answer. Okay, and another interesting thing also from doing these modelings is you see where actually is the uplift. And we find that most of it is offshore, which means that you're not only uplifting the islands, but also the water. And this is what caused the big tsunami that I guess you all heard about. Okay, so we've seen the slip distribution caused by this earthquake, but as Mark shown from the high-rate GPS, the earthquake is not something which is occurring instantaneously. It's something which is taking some time. And to get an idea of how the slip is distributed over time during the earthquake, we can use seismology. So in addition to the INSAR and the GPS, I collected some seismic measurements. So you have seismograms here collected from stations all around the world, stations in Africa, in Antarctica, in the Pacific, and in North America. And you can see in those seismograms, which are compressive waves, P waves, that there is some complexity. You can see that you have different bumps, and all these bumps, they actually reflect some big release of energy, so basically areas which are slipping more during the rupture. So by including this data, we can try to see how the slip is evolving over time. Okay, so this is a movie which is going a bit fast because it's a kind of last-minute movie, and this is because we get data every day. So you have the epicenter here in red, and you can see the slip propagating north and south, again with very large amplitude up to 19 meters. And here in this graph, which is the amount of energy over time, you see that the energy is not just released instantaneously, but has some complexity. Okay, so the reason why we are doing that is not only to understand the physics and the mechanics of the rupture, but it's also to better estimate the damage right after the event. So right now, we're 1 month after the earthquake. We are just getting these preliminary models, but in the future, we can hope to get this kind of estimates right after the event to help the relief effort to assess where is the highest shaking occurred. And I will maybe finish with this image, which is showing you the maximum amplitude of the tsunami in the Pacific. The model I've just shown before is also an effort to better predict the tsunami. And in the future, when we'll have more high-rate GPS stations, we'll probably be able to get those rapid estimates to better predict the tsunami amplitude in the deep ocean, but also along the coast, Like we know now that in some cities along Chile, they had up to 10 meters run-up, so a wave of 10 meters hitting the shoreline. In some places, they only had 1 or 2 meters, and it's a critical information for the relief effort to know where the rescue teams should go and put their effort to help people right after a big event like this one. Thank you.
Thanks, Anthony. Hope that all understood. Here we're looking at this very large earthquake. I'm now going to try and bring up the next PowerPoint for the next speaker as I'm trying to talk. I hope you wanted that saved. And you could see just how big that earthquake is. I don't know if you could see the scale at the bottom. This is an earthquake that lasted for 2 minutes, like Darwin's earthquake. And offset, the maximum offset on the fault was 60 feet. Yeah, there was 19 meters. That would be if we had the fault running down this aisle. Those of you hiding in the back would end up finding yourself up on stage after the event had happened. And that's really a very, very large event. We are now going to go in a different direction and start our look at the Chilean earthquake, which is a smaller earthquake in geologic terms, but a larger earthquake in terms of the human impact. The next speaker is Rich Briggs, who's a geologist with the U.S. Geological Survey. He also spent a time as a Caltech postdoc after having gotten his PhD at the University of Nevada, Reno. Rich.
Thanks, Lucy. So I'm going to provide get the ball rolling on talking about the anatomy of the Haiti earthquake and describe our field efforts to try to understand this event. When you take a cruise ship out of Florida into the Caribbean, they don't tell you that you're entering a tectonically active place. Maybe they should. Note the Caribbean plate here is being overridden by the North American plate at about 20 millimeters a year, just less than an inch. And that causes subduction that, as it turns a corner, becomes oblique and then into kind of a sideways smashing shear. And Haiti is stuck right in that zone. And so a closer look at Haiti, here's the Caribbean plate moving underneath the North American plate. And Haiti owes its existence to this plate boundary and all of the crunching and grinding that goes on here, microplates stuck in here. We're going to take a closer look at the southern peninsula of Haiti. The star shows where the event happened. And so here's our yellow star and Port-au-Prince, the capital. This is just a model of what the topography looks like, and you can see these gashes and tears that extend along the length of the peninsula. And what these are, it really is the plate boundary, the Enriquillo fault zone. And it's just an expression of how the island's accommodating this sideways and a smashing motion that goes on. And so what that causes are earthquakes that are large and frequent. And so we're going to, again, take a closer look at this area where the star is. So that's the epicenter. Port-au-Prince is here. And what's plotted here are the aftershocks that roughly show the area that ruptured. And notice that this is to the west of Port-au-Prince, and that's going to come up later as an important point. You can see the fault zone, a fault valley, but it becomes a bit more complicated out here. That's going to play a role later in our trying to understand this. And notice that the aftershocks are in a fairly diffuse zone. And so Lucy nicely made the comparison, and she sort of posed the question, to paraphrase her, what makes a disaster a catastrophe, or really what goes from bad to worse? And the left side shows a comparison of Chile in terms of the size of the rupture, the rectangle here versus Haiti, a much smaller portion of the fault broke in Haiti. But notice that the intensity of shaking, red here is very heavy. You see more intense shaking than you do due to the deeper fault that's a little farther offshore in Chile. And so what it comes down to really is how shallow the shaking is and how close it is to people and their structures, and whether or not the people and structures are ready for that shaking. This is that's the former library of the Bureau of Mines and Energy, and we were lucky to be able to work with them on this study. So our goal then is to develop a thorough understanding of the earthquake source and put together all of the observations we can. This is jumping the gun to something Eric is going to talk about later. We want to develop a model of how we understand things occurred, partially because we want to understand how the Earth works, but also because we want to take that understanding and apply it to hazard and mitigation. And so the part that I'm going to concentrate on is the geological aspect of this. And there's been a team down there from USGS for nearly a month. Some of the people are returning just in the last few days, and also University of Texas and the Bureau of Mines and Energy in Haiti. So I'll take a quick aside here and talk a little bit about the data that we're able to use, especially the optical imagery. Back in the old days, which we're just going to say before these two earthquakes, fabricate this a bit, but data was stored locally and was hard to process, and you needed an expert to work with it, and it was hard to pass around to your friends. So things have changed. The way it is now is a lot more complicated and chaotic, but it's also a heck of a lot more fruitful, I think, for our efforts. After this disaster and after hurricanes and similar things like this, there's an international charter that can be activated to quickly take spaceborne sensors and point these things to the disaster area. This happens in the hours after an event like this. And then that data goes to, in the case of these two events, it's gone to the USGS and has been sort of stored and then distributed out again. It also goes straight to you've all probably used Google Earth. And then this data bounces around in pretty fascinating ways. It goes to all the way from the military to just volunteers who are taking their time and efforts to take that geospatial information and make it useful quickly and reconfigure it and redistribute it. So this is a great part of how things have changed. We used a lot of optical imagery for the part of the study I'm going to talk about now. There's a lot of good high-resolution satellite data and also aerial data. And so let's jump to some of that. And the data I'm going to show you is data from Google Earth. And so you can follow along at home or look at this later and see a lot of the same imagery I'm going to show you. So one of the things we found out right away was there was no whacking big surface rupture along the fault. This is a bit of a surprise. It's a shallow event, and on a big strike-slip fault that you saw is very well defined. And so we had to. This is one of the things we need to sort out. We have lots of great imagery and nice features to be able to spot this sort of thing. We do see a lot of secondary ground cracking just due to shaking. I'll return. There is a very interesting feature we don't quite understand yet, but by and large, there's no big crack running down the middle of the ground. And if you've seen movies, sometimes those swallow trains, apparently. But what we did see, which was a surprise, was that we saw along the coast coral reefs were uplifted out of the water. And maybe not as much of a surprise, we saw lots of secondary cracking features along the coast. And so what happened was large areas of the coast were lifted up, and at the same time they were shaken and parts of them collapsed downwards. So I'm going to show you a little bit of how we can use these corals to map the deformation and the uplift. So taking a closer look at this patch of corals, here's Fred Taylor showing us where one of these coral heads, which is now with its brethren, been lifted up and out of the water and has died. The top of this thing marks where low tide used to be. And so we're able to take that information and then by making measurements, turn that into an uplift measurement. In this case, it's about 60 centimeters. So here's a closer look at one of these heads. The corals grow up, and then they can't grow up higher out of the water. They like to be underwater. So they mark more or less low tide along their tops. Then they're lifted up and out, and this is a strip of still living coral down at the bottom of that head. And so in a general sense, that's the amount of uplift. This head's actually going to die down more as there are lower and lower tides coming in the future. So we model that, and we try to understand that part of the process. But in general, we can take these observations and turn them into a map then of how the Earth moved. And so we just saw a bit of the reef that's uplifted. Over here, of course, things cracked and separated and made their way toward the ocean. And this part of coastal deformation is often unappreciated. It's a lot more spectacular when things lift up and are stranded. But it's actually a big problem to have water in your house, a big problem to have water. Even just tens of centimeters can cause pretty severe erosion along a coast. So in this case, you notice how the house over here is roof is flat and then kind of dives down toward the water. This is because of that slumping that occurred during the shaking. And then trees are in the surf and this sort of thing. So this is along about 30 or 40 kilometer section of coast that you see features like this. And this will turn out to be a big problem as bigger storms come in and just tidal effects. It's going to chew away at this coast for a while. So we take all these observations and turn them into a map. And in this case, the red dots show uplift. And so we can make these measurements and use those as part of the story about to try to understand the earthquake. Here's the epicenter of the earthquake, and this is the strike valley, and Port-au-Prince is over here. There is one enigmatic feature that we don't quite understand, and we're going to talk a bit. A thread running through our presentations here is how we can use satellite remote sensing data, and especially data that's collected quickly, rapidly after events, and repeatedly to understand things. This is a feature that we don't quite know what to make of it, and if we had maybe a faster repeat time on some of our observations, we'd know what to do with this. But in essence, what it is, it's about a 3-kilometer section along what is clearly a fault-bound ridge that had an opening, a crack that developed along it that's very continuous, but there's no sideways motion on this, and it's only 10 or 15 centimeters of offset across it, and we don't know when it happened. We don't know if it happened when the big earthquake happened, or if it happened during an aftershock, or if it happened slowly at some other time. And so it's features like this. This is another view of it out in the water where it shoots right out into the water. That also tell us something about how the Earth works, but we're not quite sure what to make of this one yet. Now, that feature was off to the left off this figure, but if you follow the fault toward Port-au-Prince, the geology teams have done a great job of mapping how this fault looks in exposure and how it comes to the surface. And it's very clear that there are recent ruptures that have occurred along here, and Ken is going to talk more about this. And it's very clear that some of these are recent. And so this is alarming when you look at the proximity to Port-au-Prince. So I'm going to finish up with those observations and say that the primary signal that we see geologically, to our surprise, is not a big rupture along the surface of the Enriquillo fault, but instead we see a broader deformation pattern and we see the coast deformed. This is telling us something about the event. And Ken and Eric are going to complete that story for you. The fault rupture was complicated, but we know that this section near Port-au-Prince remains unbroken. And rapidly collected imagery and web distribution and creative recombination is changing how we respond to these events, mostly for the better. But as Ken will point out, we still have to get out there and have that in hand and still look at things in person. Thanks very much.
Thanks, Rich. We're going to continue on this theme of doing the field geology and combining it with the space data to help us better look at this with some more work that's been going on in Haiti. The next speaker is Ken Hudnut. Ken is the earthquake coordinator for Southern California with the U.S. Geological Survey. That means he's in charge of all of the earthquake operations here in Southern California and will lead the response when it's our turn. But he has also been, we wouldn't want him to have to wait too long, so he joined a team that went down to Haiti with the U.S. Geological Survey to support the recovery method, and he's going to tell us some more about this. I would mention on a theme, Ken got his PhD from Columbia University and then served as a postdoc at Caltech. Ken.
Okay, so yes, I'm going to try to keep developing some of the points Rich was making, and in particular, I want to emphasize we've been kind of put on the spot to say something about what the future hazard is for Haiti, and so to do that, we want to find out as best we can what the past behavior of the fault system is there, and so that was the reason for going down to the field. As you can see here, it's a nice summary of what's known about the past earthquakes in the region. So remember from the slide Rich showed, there's the Enriquillo fault system along here, and also in the northern part of Haiti, the Septentrional fault system. So that 20 millimeters a year across this plate boundary that Rich showed is divvied up with actually more of the slip along this fault system. So actually, Hispaniola faces hazard from both of these major faults and probably also from some secondary faults, perhaps like the one that ruptured in this earthquake of January 12th. But it's thought, it had been assumed, that the bigger earthquakes down in this part of Haiti in 1751 and in 1770 were along the Enriquillo fault system here. So when we had this magnitude 7 earthquake, and as Rich showed, there's this big linear trough, the Momence River Valley, we thought, well, there probably will be surface rupture along it. And as Rich said, we were surprised to find that there was not surface rupture there. Well, so unfortunately, these earthquakes were long enough ago, and hurricanes are frequent enough in Haiti that building construction had kind of drifted away. People had earlier on in history recognized that there was significant earthquake threat in Port-au-Prince, but in more recent time that had been kind of lost to history, and people were emphasizing more hurricane-resistant design. So part of the context of our work in Haiti has been to figure out, well, is that it? Was this magnitude 7 all we really need to be concerned about? And so now, from now on, maybe some regular aftershocks, not much else? Or is there the specter of an even bigger earthquake, possibly even closer to Port-au-Prince? So we look to the history. We see that there have been earthquakes that basically leveled Port-au-Prince in early historical time. And we wanted to go in and then also evaluate this fault system and see if we felt that it was capable of bigger earthquakes closer to Port-au-Prince. So we needed basic geological information to inform these decisions about how to rebuild Haiti, how to do a better job of building seismically resistant structures. And we needed to provide a seismic hazard map to guide good structural engineering and efficient structural engineering for the construction of these new buildings. So we needed to search for sites that were suitable for getting a long-term geological slip rate, and we also wanted to find sites where we could determine the paleo event history by looking at disrupted strata and doing radiocarbon dating of prehistoric events. So we needed to find sites that were suitable for these kinds of further study. And we also wanted to search for evidence of these early historic events or prehistoric surface rupturing events. So as I mentioned, it had been assumed that the Enriquillo fault system had generated these big, damaging early historic events, but nobody had gone and actually done the field work to try to associate offsets along that fault system with these earthquakes. So that's what we set out to do. And it was with our colleagues from the BME. Rich showed you the photograph of the collapsed building. That was their headquarters building. That's the counterpart agency to the USGS in Haiti, and several of their people were killed in that collapse. But we were, as Rich mentioned, we were able to work with Fedi Jean as part of our group in the field. This just gives you a quick summary of what we propose to do as an initial phase of investigation of the geology of this fault system. So this is work that was funded by USAID, and it breaks down the coastal effort that Rich talked about, and then the search for surface faulting in through this area where the main shock and all the aftershocks occurred. We then extended that out to look first towards the east for evidence of early historic rupture, and also to look at whether we saw patterns of slip along the fault that might link it to slip in the 1751 or 1770 earthquakes. And then to get a complete picture, a synoptic view of the whole fault system, we also wanted to extend out and do reconnaissance mapping of the fault system all the way out to Tiburon in the west. And so this is what we set out to do, and for the most part we were able to accomplish all of these tasks already. As you'll see, there's a lot more that we need to learn, and some really tantalizing places that we found along the fault that demand further work to get the most out of these sites. But furthermore, I should mention task 4 here was to evaluate the landslides induced by shaking in this earthquake, and that work has also been, the initial phase has also been completed. So we've been talking a bit here so far about the satellite imagery, just fantastic high-resolution satellite imagery that we were able to bring to bear in looking for surface rupture early on. And then after that, a tremendous amount of airborne imagery was also acquired, and Rich mentioned some of this. One of the especially useful data sets for us was the LiDAR data, airborne LiDAR data collected by the Rochester Institute of Technology along with a company called Coursera, funded by World Bank, and ImageCat was heavily involved with organizing that work as well. This whole data set is available openly on their Rochester FTP site and also through opentopography.org. So this is an index overview figure from OpenTopography, and you can just go in and zoom in anywhere within this imagery and look at very high-resolution topographic surface models along this whole fault system from the area where the main shock and aftershocks occurred all the way out to the Dominican Republic border. So this whole eastern section we were able to look at in the LiDAR data before going down to the field. And also while we were in the field, we were able to make further use of the LiDAR data. So this is a relatively new technology that we're using more and more. And actually, what works best is to have pre-earthquake LiDAR like this, high-resolution topographic surface models, and then after a big earthquake occurs, do it again and again and again, and then we can capture the co-seismic pattern of deformation in great detail and also the post-seismic deformation. So that's something that we hope to do in future earthquakes more and more. This is actually the third example of an earthquake that has had its post-earthquake image taken with LiDAR. This occurred also with the Hector Mine earthquake in 1999 here in Southern California, and also the Denali earthquake. So with just the post-event imagery and a big surface rupturing earthquake, you can learn a lot from LiDAR. But we're hoping to use the before and after differencing as a future way of getting even more information on earthquakes. Okay, so for Haiti, we were able to use this LiDAR data set to look, as I said, we were searching for sites where we could get long-term geological slip rate information. This is the closest thing we found to something like the equivalent of Wallace Creek on the San Andreas. Some of you may know this is a big offset dry creek bed channel out in the Carrizo Plain that we have on the San Andreas. And here in Haiti, we found in the LiDAR data this offset channel. So the upstream part of the channel, it's dry now, but it used to flow down to the fault, and then it was deflected through time by many earthquakes along the fault, a total of just over 160 meters. And this is the downstream part of the channel. So this is the left lateral deflection of the channel that we were able to identify in the LiDAR data. We then went and, of course, had to field check it and look and see whether this really hung together, whether it looked correct in the field. And so this is a tracing of the channel here. This is the upstream part flowing down and then deflected like so, just looking at it from a different angle. And yet another different angle here, the upstream part flowing down, deflected, and then like so. We were actually, under Carol Prentice's direction, she was able to organize to get trenches dug here and also here. And unfortunately, in these trenches, we did not actually exposed the fault. So what's going on here? What we think is that the rate of sedimentation here has been so high that perhaps this uppermost 2 meters or so in the trench wall is not actually broken by the most recent earthquake. It could be that the sedimentation rate is so high that it's just all been covered up. So on a future trip, we may decide to go back and dig deeper to try to expose the fault. The fault probably, we were expecting to encounter it right down and about here. So now we're left with that reality that we see this big offset, but we don't know how old that is. We're still trying to get at that, so it's going to take more work. We found some other good candidate sites for trying to get a long-term geological slip rate. By the way, the reason we want to know the geological slip rate is that the only information we currently have about how fast this fault is being loaded is from GPS measurements in between the times of earthquakes, indicating that the fault has a slip rate of about 6 millimeters per year left lateral. So we want to get a geological estimate of the slip rate to basically bolster that information from the GPS. Typically, when we make a seismic hazard map, we rely very heavily on a good geological slip rate for a fault. And we just don't have one yet for this fault system. So here is that big offset channel that we've had a hard time dating. Here's a smaller offset. We'll take a closer look in a moment, but also revealed from the LiDAR. This is an offset river channel edge. So this river channel, we think, used to flow around this corner and then go like so, straight, but that through time, the fault comes right through here. We think that it's been deflected left laterally. So here is the offset channel, and then similarly, here is this offset channel margin. And this is at a site called Jameau. So the site here, coming across, this is the offset I just pointed out, and here is a big exposure of the fault surface, which Rich showed earlier. It's dipping toward the south at about 70 degrees here. It's also exposed over here, dipping to the south. So the fault cuts across right through here, and this is the roughly 30-meter offset here. Ryan Gold here is showing the people that live nearby the LiDAR data and explaining why it was that we were so interested in what we were trying to learn. And we had their help in excavating a pit to examine the soils here and to try some different techniques for dating it. Let's see here. There's a tracing of the fault, and then this is that offset feature with an orange dashed line here. And then these little blue ovals, this shows the soil pit. And then these are some large basalt boulders that are in place in the surface. And we took the caps off of these boulders and brought those samples home to try to do cosmogenic exposure age dating to try to get at the age of this surface. So again, we're still trying. We don't yet know the age of this surface, so we don't yet know the slip rate here. But we're pulling out all the great tricks that we've developed in studies of earthquake fault zones worldwide and applying those relatively new methods and hoping to get at the geological long-term slip rate here along this fault system. Another thing that we did was we were able to sort of crank up the resolution on our imagery by taking oblique air photos out of helicopters as we were doing our field work in Haiti. This aerial oblique photography out of the side of the helicopter is another technique that was developed by Dave Lynch and myself here in California. Basically, we can, with a consumer electronics grade or slightly better camera with a GPS attached to it, we can get imagery that's a factor of 10 to 100 times higher resolution than the very best typical airborne imagery that we were getting. So we then use this to further our search for good slip rate sites and good offset channel features along the fault. So this just shows that at a zoomed out level, it shows you our basic coverage. So we have nearly 10,000 oblique air photos shot out of the helicopter, open doors and open windows along the whole fault system. And as you zoom in, you get a sense of just how many photographs we took. Zooming in even more at this site of interest, you see that I kept shooting as we went up and down this channel where we knew that there was this offset we'd seen in the LiDAR data. And I just kept taking photographs about every half second. And here you see the ground tracks of our flights as we went up and down that channel, just photographically documenting the offset. Here's the offset, how it looks in the LiDAR data, the fault going across here, and an older terrace level up here, a younger one down here. and we actually were able to not only photograph that from the air, but also get on the ground at this site. So here you see that same site that we were looking at in the LiDAR just now. This is the upper terrace surface. It's offset by about 6.6 meters. And then the lower, younger terrace that's set down in the main channel is offset by about 4.8 meters, and the fault goes right through here. And so this is just yet another site where we hope to be able to date the older and younger surfaces and get an age constraint on those smaller offsets. Yet another thing that we were able to do is find small offset channels that we think are indicative of slip in the latest earthquake on this fault system. So this magnitude 7 did not produce surface rupture. What we think is that this early historical event, which is thought to have been a magnitude 7.5 in 1770, probably produced the slip that I'm about to show you, these small offset channels. So here you see the Enriquillo fault comes across this channel here, and Carol Prentice is standing in the upstream part of the channel. And here's a little tracing of the deepest point of that channel as it comes across. It's actually, in total, it's offset by about 11 meters. So if you were to project this upstream part down to the fault over here, it's offset about 11 meters over to here. But that's representing several earthquakes slip. The latest earthquake, we think, is represented by the slip from where Carol's standing over to this low point in the channel here on the downstream part of the fault. So this is about a 3-meter offset here. And in all, we found 9 such sites with small offsets ranging from about 1.3 up to 3.3 meters of slip. Here, the fault is coming through the picture like so, and they're measuring the offset here. And in other places, some of these small offsets were in such thick vegetation that even the LiDAR imagery, which can typically penetrate through the vegetation, just wouldn't be able to see these small offsets. We had to get down on the ground, and that was part of my subtitle, was that imagery isn't everything. We can't learn everything we want to learn by taking pictures from a helicopter or an airplane or a satellite. You've got to get down on the ground and make these observations in the field, and you've got to verify your imagery analysis as well. So here, several examples where, in all of these cases, really, the vegetation would have been too thick to pick these up just strictly from airborne imagery. But that was just a key set of observations, really giving us strong evidence now, which we really were lacking before, that this early historic event was a large surface rupturing event, and so we know that this fault system is capable of an even bigger earthquake. Yet another example of here, incised in bedrock on the upstream side and offset over to here. So new construction is already underway in Haiti. You can see the rebar and the concrete forms in place here. So people are not waiting for instructions from others. They're going ahead. And yet there is also a race to get good information to inform decisions about structural engineering for the future in Haiti. And the State Department very quickly put up the results of our recent workshop here that was held right after we came out of the field. And here we are meeting with our Haitian colleagues to review the issues. And this is all leading up to a UN donors conference where they're going to try to raise $11.5 billion for the reconstruction effort in Haiti. So we're trying our best to inform these decisions with scientific and engineering information. And just a final quick thank you to Fedi Jean from BME, Remu Arbouet, and Richard Boyer, who helped us tremendously in the field, and also to for all of the helicopter support from Helidosa and also the U.S. Navy and Southcom. And this is just one parting shot, one of our airborne images of a sag pond where, with further work, trenching, we may be able to get a more complete prehistoric record of earthquake activity on this fault. So we think the hazard remains high, not only from aftershocks, and we think that there's a real possibility of a magnitude greater than 7 event, even closer to Port-au-Prince, something like the 1751 or 1770 earthquakes. We're continuing to look at imagery, trying to identify sites that would be useful for obtaining more information on past earthquakes and on slip rate for this fault. And more generally, LiDAR and other imagery can be very useful for assessing damage, assessing the situation after an earthquake, damage to lifelines as well, and in general also very helpful for making geological assessment of the earthquake source and surface faulting. here are a couple of quick links for more information. That's it. Thank you.
Thanks, Tim. Okay, we're coming into the last round here. We've been looking at how the field geology can make use of the remote sensing data to do a better job at what they're doing and being able to find it a lot quicker than they could be doing it in any other way. We're now going to come to our last talk where we're going to look at how we can put together this information from space and from the field and really try to understand, come up with a model of what the earthquake is like you saw a couple of talks back. So our last speaker is Eric Fielding, who is a research geophysicist with the Jet Propulsion Laboratory, got his PhD at Cornell University, and I really wanted to be able to say was a Caltech postdoc, but I can't do it. So Eric, come and tell us about work. He's been doing work on using satellite-based radar for studying earthquakes, several past ones, and we'll hear now what's going on with Haiti. Thank you.
I won't go through all the names here on this slide, but this is work. It's been in collaboration with a large number of people, both here at Caltech, at JPL, the U.S. Geological Survey, and a visitor at Caltech that's from Japan. I'm going to be talking about the seismic data and the imagery data for the Haiti earthquake. I've grayed out these lower, the optical imagery and LiDAR imagery that Rich and Ken just talked about, because I won't be talking about those. The main earthquake seismic data was recorded by the Global Seismic Network. As Anthony described, we record seismic waves around the world to measure what happened during the earthquake. In this case, there was no local network installed until after the earthquake. And then we'll also be talking about synthetic aperture radar imagery that was acquired by satellites and by airplanes, the new UAVSAR system. By using SAR interferometry, as Anthony explained earlier, we can measure the motion of the ground surface. And what we measure is the amount of motion in the direction that the radar is looking at the ground. But by taking radar images from two different directions, then we can actually separate the motion in the vertical direction from the motion in the horizontal direction. So in this particular case, we were fortunate to have images before the earthquake from two different directions, from the JAXA ALOS satellite. And by combining those two images, or actually taking the difference, we can estimate the amount of motion in the east-west direction. So the green star here shows where the earthquake epicenter was, determined by seismology. The green line is the Enriquillo fault that Ken and Rich just talked about. And the blue area here is the area that moved towards the west. And the pinkish area is the area that moved towards the east. The scale here is in meters. This area up here moved as much as 50 centimeters or half a meter, or about almost 2 feet to the west. Another area, the area to the south of the fault, moved somewhat to the east. The first thing we could see is that the earthquake started here, but most of the motion is to the west, and that indicates that this part of the fault here, as Ken just described from the field work, this part of the fault that's closest to Port-au-Prince, which is over here, did not rupture. The other thing to notice is that there's no sharp line or discontinuity in the motion here. It's actually spread over a distance of several kilometers. And that's an indication that this fault during this earthquake only ruptured at depth. The other thing to notice is that there's this part of the coastline here that's south of the map location of the fault also moved to the west, and that's an indication that there may be a second part of the fault that's actually further south than what was previously mapped. by taking the two look directions and adding them, then we can measure an estimate of the vertical motion that happened during the earthquake. So this is a map of the vertical motion, and we can see a map that's very similar and matches almost exactly with what Rich measured by looking at corals along the coastline here. But we can see that that uplift pattern actually extends well inland, and it actually crosses the Enriquillo fault zone and extends somewhat to the south. We also see an area of subsidence or area where the ground moved downward during the earthquake. And this is actually a little bit surprising because this is actually the higher mountains. So in this case, the area of uplift is low and the mountains went down. So we're a little bit confused about exactly what's going on with this earthquake. And we're still trying to develop a model for the exact fault geometry. Unlike the subduction zones where we have a large number of earthquakes that are large enough to be recorded around the world, the previous earthquakes in this area don't tell us where the fault zone is. So in this case, we have to make assumptions about what the fault geometry is and try to estimate what the slip can be on that fault. So this is a fault model that primarily calculated by Anthony from seismology data and from the INSAR data. So by optimizing the fault model, slip model, we can actually determine both the location of the slip and the timing of the slip. This is a fault plane. At this point in our modeling, we're still using a simple single fault. That's sloping to the north, dipping to the north, and projecting to the surface somewhat to the south of the main Enriquillo fault. And we can take a look at the slip in more detail by looking at the fault plane here. This is looking at it from the north, so that west is now over here on the right. And we can see by these white arrows which direction the north side of the fault moved relative to the south side of the fault. The red star here shows where the earthquake started. And where the earthquake started, the fault slip is primarily horizontal or strike slip motion. And then you can't really see very clearly on this particular plot, but there's some fine lines here. After 5 seconds, the fault rupture reached here, and after 10 seconds, it reached here. So in fact, one of the things we can learn by combining the SAR interferometry and the seismology data is understanding how far the earthquake ruptured in how much time. In this case, it ruptured in 10 seconds, it ruptured about 30 kilometers, which is a relatively fast rupture, which may explain why the shaking was so strong, because it ruptured very quickly and intensely. And we can also see in the western part of the rupture that the arrows are going mostly up. That means it's a thrust motion or contraction that's in the direction that is causing the uplift of the coastline that was observed in the coral data and the SAR interferometry. So it's this complexity of motion here that probably explains why this earthquake did not rupture up to the surface. In fact, we can see that the slip probably stopped at least several kilometers beneath the surface. So Rich showed this model earlier. This is taking that slip model and doing a detailed prediction of what the surface deformation is with a big area of uplift, mostly out in the ocean, and then a subsidence to the south, and this westward motion near the city of Leogan. There was also measured by a GPS station there. We also, after the earthquake, flew a new instrument that's called the UAV SAR for the uninhabited aerial vehicle synthetic aperture radar. It's quite a mouthful, but UAVSAR is shorter. It is intended to be installed on an uninhabited aerial vehicle, but presently it's been flown on a piloted Gulfstream airplane. And they flew a number of flight lines over this area to get the whole length of the Enriquillo fault, so that if there is a new earthquake on this fault, we'll be able to get a very detailed map of what happened after in the next earthquake. And we can also use this imagery to better understand what's going on with previous earthquakes. Another high-resolution satellite system is called Cosmos SkyMed. This is a network of a constellation of satellites that's been launched by the Italian Space Agency. There's actually 3 of these satellites in orbit now. They're getting ready to launch a 4th one. And they have a mode which can produce very high-resolution imaging. And this is the city of Port-au-Prince here. And we can see very large motions of the ground surface here of several meters as a lot of this material that's built on fill in the city has moved out into the bay. In fact, at the Miami meeting that Ken mentioned last week, somebody showed an old air photo. All of this land here was a natural swampy bay area just 40 or 50 years ago, and now it's all been filled in with a population, but that fill has moved around drastically during the earthquake. This imagery is extremely high resolution, 1 meter resolution. So this is the image from before the earthquake. And this is the dock area, the main dock for the Port-au-Prince port. And there's another big pier here where the ships would tie. And we go back and forth here. You can see this big section of the pier has disappeared. And this other part of the section has also disappeared. This is a big crane that used to lift the containers out of the ships. It's fallen into the water. There's another crane here that's fallen into the water. And we can also see some of those lateral spreading deformations along the coast here, just with this very high-resolution imagery. And by doing a very detailed matching of these 2 images, we're able to measure the relatively small motion. This part of the pier that did not fall into the water still moved as much as half a meter or several feet out into the bay, although it did manage to hold together, probably because it's tied to this island. So by using radar imagery, we're able to measure the deformation of infrastructure and the earthquake deformation. In this particular case, because there was no surface rupture, the SAR interferometry was the key piece of information for understanding where the earthquake rupture was and what type of earthquake rupture it was, because the ground observations were not conclusive. We've also been able to start looking at the deformation after the earthquake. The ALOS satellite collected imagery less than a day after the earthquake. This is part of that international charter activation where they acquired imagery less than a day after the earthquake. This particular satellite has a 46-day interval of repeating, so we had to wait 46 days for the next image. This then shows the ground deformation during those 46 days after the earthquake. There's an area here which seems to have continued to move upward to the east of the epicenter. This may have been uplifted in an aftershock, or it may have moved with a more gradual motion. But there's also very substantial motion here along the coast. Here, these red areas are all areas where the coastline material has continued to slide out into the bay. Rich showed some of those field photos of those places where the the shoreline is slid out into the bay, and the SAR interferometry is showing us that that motion out into the bay is continued during the month and a half after the earthquake. And this is a UAV SAR interferograms. The UAV SAR has actually flown over this area 3 times since the earthquake, once in January and twice in February. This was the first 6-day time interval, and this is a 17-day time interval. And we can see this deformation here is about 6 centimeters, where this part of the delta is slid further into the ocean by 6 centimeters during just a 3-week period after the earthquake. In the future, we're going to have a much more capable satellite system. The ALOS satellite that we have been using has a 46-day repeat, so we actually had to wait more than a month after the earthquake to get those images that I just showed you. In the future, we'll have this satellite called Destiny that NASA has just decided to fund. And with that system, we can image areas, most of the Earth, within 2 days, and in many areas within just 1 day after an earthquake. So in the future, we're going to be able to produce these images instead of waiting a month, maybe only a day or 2 after an earthquake. So as to wrap it up, we get to the same slide that Mark showed at the beginning. We, in the future, are going to have this flood of data, and we're going to need a very capable system for processing it and providing it to the decision makers that are going to be able to use it with a short time delay. Thank you.
Thank you, Eric. Why don't you go and sit down? We wanted to have a question and answer period, and I'm going to ask all of the speakers to come on up to the stage. We did say, however, we were also going to get this done in 90 minutes, which we've pretty much already reached. So those of you who need to leave, feel free. Those of you who would like to ask some questions, let me get all the speakers to come up. And there are microphones right here in the front that anyone who would like to ask a question, come along and do this. I will start as people, feel free to leave if you need to, come and get in line if you want. Well, we have some questions from the online one, and I'm going to combine 2 of them. One is that, does any of this new technology bring us closer to predicting earthquakes? While as someone else phrased it somewhat differently, what types of studies do you think would be important in the future to help us understand and predict the earthquakes? Mark, you're nearest. I'm going to grab you for this one.
Right, that's a great question. It's also a very common question. I think what we're going to find is that our ability to use these kinds of observations to understand what's going to happen in the future will indeed increase dramatically. The question of what we can do in terms of prediction is a very complicated one. We can certainly do a much better job of trying to predict where the next large earthquakes will occur, and which areas should be expecting large earthquakes versus which areas probably have less likelihood of experiencing such events. The issue of predicting when these large events will occur it's a much more challenging issue. You've got to remember that the time for the system, the characteristic time, is hundreds to thousands of years. And we only get to take a glimpse at these systems over periods of 5, 10, or 20 years in most cases, if you don't include Darwin in your discussion. And so I think what you're going to find is that our ability to forecast statistically areas with high risk over the next 30 or 40 years is something we can do, and it's something we can react to. We can build the appropriate buildings and educate the population appropriately. If the question is instead being asked whether or not I should send my daughter to school tomorrow for risk of an earthquake, that's a whole different issue, and I suspect that is a challenge which will remain outstanding for very many years.
Thanks, Mark. Can I have the first question?
Yeah, it was mentioned that I think in the Haiti quake, the rupture speed was something like 30 kilometers in 10 seconds.
Correct.
Does that mean there was some sort of super shear shock cone at all, or?
That's just below the shear speed, so it's not super shear.
Not quite there. Okay. And my second question was, there's a lot of people trying to contribute to the emergency or the disaster response effort at sites like crisiscommons.org and stuff like that. What sort of information would be useful to provide to these folks in how they're doing their work as far as the recovery effort?
I can take a quick shot at that at least. One of the things that we learned about when we were trying to understand what is the use of these data for emergency response was, in fact, the impact of social networking infrastructure for responding to large events. One of the actions that impressed me a lot was that they used all this high-resolution airborne imagery and to actually map out which buildings on a building-by-building basis were destroyed. The problem is that the area is quite large, and so they didn't have the human power to look at these images in standard institutions. And what they did is they cut up the images into 600 tiles, and the Earthquake Engineering Research Institute got many earthquake engineers to volunteer, some 600 of them, to each look at their 1 kilometer or 500-meter tile. And using a few guidelines, went through and actually mapped on a building-by-building basis, totally destroyed or has obvious damage. And that information was then used by the ground crews to go out and actually focus where they should spend the most time. Now, that's all good for magnitude 7, which is admittedly a small earthquake on the scale of some of these events. And the problem is when it becomes a magnitude 8 earthquake or larger, the area involved is as you saw in the example for Chile, much, much larger. And so my own bias is that while this social networking infrastructure is going to be very important and will continue to be important, we have to do a much better effort at automating the detection methods that we have for looking for damage for disaster response and being able to help guide the field crews in their ground-based assessments. And that's possible. It just requires a lot of software engineering and careful thinking about the process.
I want to, one more question here and then one more from online.
My question is, we keep hearing about magnitude 8.8 and 9. Who decides that magnitude in what proportion? And do I expect to have a magnitude 50 if it's possible? And just my question.
Ken, you want to take that one?
Sure. So magnitude determination is something that USGS does for global events, but other organizations do as well. So, for example, if there's a big earthquake in Japan, they will determine the magnitude. And so the USGS has gone through all of the historical earthquakes and done the best that we can with data available to basically re-estimate and come up with final answers for the magnitudes. But when a big earthquake happens, like the Chilean earthquake, it's very common for the initial magnitude to be off by a bit. So you'll see that happen, that the initial estimate might be 8.3, and then it'll bounce around a little bit and then settle in. So as Mark showed, as Professor Simons showed early on this evening, the magnitude is really a relative measure of the size of an earthquake with respect to other earthquakes. It's a logarithmic scale. There's no hard top end to it, but a magnitude 50, like you suggested, is basically it's inconceivable. Even if the Earth were to crack into 2 halves, I'm not sure the magnitude of that. It'd be
I think
probably
that's about a
like
13 we once
13?
figured out.
Okay.
Yeah. Yeah.
So hopefully that won't happen. Wasn't there a movie about that recently, the 2012? But don't worry about a magnitude 50. Do worry about events smaller in magnitude but closer to population centers, like what happened in Haiti. It doesn't take a magnitude 8.8. Even a magnitude 7 in the wrong place can be a really bad one. part of the emphasis tonight was on how we're getting better and better at getting accurate information rapidly. We're getting better at determining magnitudes, hitting the nail on the head quickly. We're doing better. But we're also doing things like combining information about the shaking pattern that's just happened in an earthquake with our data on the population centers. And so USGS has a product out now called Pager. And for the Haiti earthquake, it was out within 20 minutes, a very accurate estimate of the levels of shaking of different intensities and mapped onto the population distribution. So that's actually a very useful way to get a quick indication of just how serious an earthquake was. And similarly for the Chilean earthquake, it was a pretty rapid, accurate estimate as well. So anyway, on magnitudes, it's an art. Well, no, it's a science.
It's a science.
Why don't you say Lucy's an expert on this? So.
Yeah. There's a question that came in on the web that I want to ask. I think it might have actually come in before Ken's talk, because it said, have any paleoseismological studies been done in either of these two event areas? And of course, we saw what Ken had to show us about paleoseismology studies in Haiti. Do we have information about Chile? Do either you or Rich know? Or
yeah, so of course, we have the historic record from Darwin. But there has been a lot of work looking at uplifted sea terraces all along the coast of Chile. And those have indicated that there are actually good evidence for large earthquakes in the past, as should obviously be the case. More interestingly, there was actually a study that was published a few years ago where they looked at the distribution of sediments from tsunamis, or the tsunami deposits. And so they went because a tsunami, of course, brings in sand and other foreign material fairly far inland. And so by going into these low-lying areas, they can then go back in and map out which areas experienced large tsunamis in the past. And so, for instance, the Chilean 1960 earthquake has had other magnitude 8 earthquakes in the last few hundred years, but the preceding very large earthquake that had tsunami deposits the same size as the 1960 earthquake was about 300 years ago. And so these kind of studies are ongoing and, of course, depend on the availability of geologic sites that are amenable to this kind of study.
Okay, good. Sir?
So my question is relating to what happens after the earthquake and the damage. And there was a comment made earlier that some of you would be a part of the planning organization or effort after the earthquake. So we've now experienced two relatively catastrophic events. We've learned a lot through history on the kind of damages that occur. We live in California on these tectonic plates where there's propensity of a big one occurring. In your estimate, have we learned enough in terms of the propensity of most probable damage? In the Haiti earthquake, there were examples of roofs collapsing. Do we have people trained to get us out of those circumstances on large scale? Do we have equipment such as, I'm a layman thinking, helicopters that can lift heavy weights? Are they stationed in a position that if people in California are affected, that those crews can be put to work soon enough to help a large population? So I wanted to find out if this is the right forum, if you are people who would be affecting strategy and public policy to be able to make a difference in that direction.
Maybe I should take this one. Yes, some of the best urban search and rescue efforts are stationed here in Southern California. The Los Angeles County Urban Search and Rescue Team is world-renowned, spent a couple of weeks in Haiti, rescued 150 people live from the collapsed buildings there. They go to those type of events around the world to maintain their training. We luckily don't give them a lot of practice here. At the same time, we are unlikely to have the level the amount of collapsed buildings that we see in Haiti, because we have had more effective building codes over the years. I would rather strongly state, however, that when we look at those sort of issues, the issue is not how much we have learned, but how much we're willing to pay to enforce. It's not a matter of whether we know how to make a strong building. It's what we're willing to do about a building that we know is weak and is still standing, and whether or not we're willing to require its owner to retrofit it, or how we're willing to take on those issues. Concrete buildings, as we've seen in both of these earthquakes, can be very deadly. Unreinforced masonry is the worst. We have a retrofitting law in California to try and retrofit old unreinforced masonry buildings. We have no other retrofitting requirements whatsoever. We have considered it completely voluntary. We are unwilling to tell a building owner they have to spend money on their buildings. And therefore, there are a lot of buildings out there that we know are going to fall down. And we have to choose to get rid of them. And that's the fundamental issue, not whether we know about it. Sorry, a little bit of a high horse there.
What about equipment such as helicopters to lift roofs and rescue people?
No, you're probably going to, that's a pretty dangerous way to get somebody out, because the structure is unstable. So the urban search and rescue teams have extensive equipment, but they burrow in rather than trying to pick the stuff off, because you pick up one layer, you don't know what you're going to destabilize underneath.
All right, thank you.
In earlier years, I learned that it took me about 5 seconds to go from a dead sleep to run to my children's bedroom to make sure they were safe. So I always thought, now that we've done so much with our internet communications, can we set up a fast warning, it's going to hit in a few seconds? I mean, we could all do a lot of good things with our safety with even a short amount of time.
That fits back in that category of what are we willing to pay for. Do you want to say a little bit more, Ken, before? Or
Sure. So that's another new technology that we're very excited about, what we call earthquake early warning. And the concept there is that as the waves are traveling towards a big city, you can outpace them. And so with telecommunications, you can basically send information at the speed of light, more or less, through wires or through wireless telemetry. And so if we have sensors close to where the earthquake starts that pick up that earthquake and can say, it's not just a little earthquake, this is big, send that message down to, say, Los Angeles and set off some kind of an alert system. That's something that we're able to do. We can't predict earthquakes, but we can do early warning, but it just takes a lot of money. So we're currently developing that technology at a pace that we can afford, but we're very excited about the possibility of maybe getting increased funding so that we could accelerate that development effort. And I think that actually probably within the U.S., Southern California is the place where we're going to first do earthquake early warning. We're trying and we're working in that direction. Lucy's been one of the leaders in this, but it's a joint effort really of Caltech, USGS, as well as Berkeley and Southern California Earthquake Center. So some of the most promising algorithms, methods for doing early warning are actually, well into a test phase. We're into the next phase where we're going to be doing earthquake early warning in a testing mode, and we're starting to work with partner organizations that feel that they have the wherewithal to be able to use that message. But we're a long way from actually what we would call operational use of an early warning system here. In Japan, they're doing that now nationwide, and in some other countries they have early warning systems that have been operational for years. So we're kind of behind the curve, and we'd kind of like to get ahead of the curve on that.
Thank you.
Yeah. Japan spent $600 million establishing their nationwide earthquake early warning. We think we can do it for $100 million, but we don't have that at this point. I'm going to take this last question, then we'll wrap up. If you have other questions you want, we're here, but I think it's time to pull this to a close.
This would kind of be segueing on that last question. I just come to find out that the normal laptop and personal computers have a type of accelerator that could actually allow people to, with the proper censoring, help and I guess forewarn as far as earthquakes go. Is that something viable? Could we lead in that, or is that going to be too confusing as far as things possess?
Do you know?
Yeah, so that's actually a wonderful question. There is a lot of ongoing research right now at the academic level here at Caltech, at other universities, at Stanford and Riverside, on using the accelerometers in your laptop or using cheap seismometers that you can have on a USB stick and leave on your desktop. And instead of having the very expensive sensors of which we do rely on to distribute throughout California, we could have, instead of a few hundred of those, we could have thousands or tens of thousands of these cheap sensors in everybody's home. And so it becomes then a software engineering problem and a computer science problem of how you manage lower quality data that's a lot more pervasive. And when you have tens of thousands of slightly lower quality observations on machines that can be moved around, that sometimes don't work, that somebody unplugs, somebody drops their laptop or whatnot. And so it's a wonderful question because, in fact, it is really the future, and there's a lot of effort going on to use this technology to help you, in fact, image the wave field just because of the density of machines that you have in people's homes, especially in urban environments.
Okay, well, thank you all for coming, and I hope that you've gotten a bit out of this, and I'll be ready for the next earthquake. Thank you.